All right, note card 42. For all my artists out there, we are going to be doing some curve sketching. This is a fun process, but it is very detailed. So go through your checklist every time. We are going to learn how to curve sketch. All right, so when we're curve sketching, we are going to use all of that information that we have found over the last week, and we are going to use that to draw a picture of our curve. So we don't need to depend on our graphing calculator anymore. We have enough information that we could draw a good sketch of our curve, so you have a decent idea of how it's behaving. Okay, so here are your steps. Go through your checklist every time. Eventually, this will become ingrained in your memory, and you won't need your checklist. But for now, first we plot any given points. Okay, always start with your givens. Then we find x and y intercepts and vertical and horizontal asymptotes. That's going back to Algebra 1, Algebra 2. Okay, find critical points. What are our critical points? Remember, those are where our first derivative equals 0. And then where it's increasing and decreasing, so we're gonna have to draw our number line there. Local max and min points, right? From finding our critical points and then plugging it back into our original. Determine concavity, that's what we were just doing with our second derivative and our points of inflection, and then we sketch in the curve, okay? So let's get started. All right, so working with my checklist here. First, it says plot any given points. I am not given any points, okay? Then find x and y intercepts and vertical and horizontal asymptotes. Okay, so remember my x-intercepts would be where this is equal to 0, right? So I want to find where this is equal to 0, which would be at 1. So I would have x-intercepts at 1, 0. Okay, and then my y-intercept is what happens when I plug in 0. So if I plug in 0 here, I would get -1. Okay, so there's some good points for me. Vertical and horizontal asymptotes, those come from a denominator, and I don't have a denominator happening here. So I don't have any asymptotes. That makes this a little bit easier for me here. Now, find critical points, and that leads us to part A. So this actually comes from this 1977 AP Calculus exam. What was happening in 1977? We are going to ask for what values of x is f increasing. So here we go, we're at step 3. We need to find the critical points, draw our number line. So f prime of x. Okay, it's very important in this to keep all of your work super organized. Okay, so sometimes what I do is I make like a little box over here. I call it my sidebar, and I stick all of the points that I find, any important information in there. So like these are my 2 points that I know I'm going to have to plot. First derivative, clearly labeled. I need to do chain rule here. So I have 3 times, keep the inside the same. This becomes a squared times the derivative of the inside, which is 2x. And I need to find where that is equal to 0. So I'm going to take each piece separately and set it equal to 0. So x squared minus 1 has to equal 0. 2x equals 0. So on my number line, I would have -1, 0, and 1, right? -1 and 1 both coming from this piece here, 0 coming from this piece here. Now I'm going to plug it back into my derivative in order to find where it's increasing or decreasing. So here we go. For my derivative, we've got, if I plug in -2, I would have a positive times a negative, which would give me a negative. If I plug in -1/2, that would give me a negative times a negative, which would be a positive. Positive 1/2 would be a negative times a positive, which would be a negative. Right? Did I do that right? Yes. And then if I plug in a positive number, this is going to be positive. Oh, but I forgot about this squared. Hold on. Go back. Double check me. So if I plug in -2, yes, that'd be positive, times negative, yes. Here, I would have technically a negative in here, but then it would be squared and a negative. So this actually is negative. And then if I plug in 1/2, I would have this is always going to be positive right here because of that squared. So positive times positive would be a positive, and then positive there as well. Okay, so whoops, caught my mistake. Be super careful when you are doing that. And on to the next. So it asks us for what values is f increasing. So we are increasing from 0 to 1 and from 1 to infinity. Okay, is the answer for part A. So for part A, we are increasing from 0 to 1 and from 1 to infinity. Okay, then we want to find the x and y coordinates of the relative max and relative min. So I have got a minimum happening here, right? Because I'm going from negative to positive. So I've got a minimum happening here at 0. I want to plug that back into my original, and when I plug that in, I get 0, -1, which, oh, look, it's already there. So my y-intercept just so happens to also be my relative minimum. And then I don't have a relative maximum because there's nowhere that I'm changing from increasing to decreasing. So then we'll actually write out our answer. So for part B, we have a relative min at 0, -1. And then we would say because it's where f prime of x changes from negative to positive. Okay, so that's enough for our justification there, right? We're changing from negative to positive. Our derivative there, which means we're changing from decreasing to increasing, which is a minimum. And we do not have a relative maximum. Okay, so there's the answer to part B. For what values of x is the graph concave up? Here we go, part C. Okay, so for part C, to find where it's concave up, I need to take the second derivative, which is going to require a bit of product rule here. So I would have, this is my first and this is my second. I have the second times the derivative of the first plus the first times the derivative, let me move this, it's not this, there we go. The derivative of this one would be chain rule times derivative of the inside. Okay, so I would have 6 times x squared minus 1 squared plus, I would have 6 times 2 is 12 times 2 is 24, x squared times x squared minus 1. Okay. Then I could factor out an x squared minus 1. So x squared minus 1 times, I would have 6 times another x squared minus 1, because I used one of them, but one was left, plus 24x squared. And the reason I'm doing this is because I'm going to have to set it equal to 0, and I couldn't figure it out from up there, right? I want it in a factored form. So now I can simplify this. I would have x squared minus 1. This would be 6x squared minus 6 plus 24x squared. So I'm going to have some like terms I can combine. Here I have 30x squared minus 6 equals 0, and x squared minus 1. So then from here, I would have that x would equal 1 and -1. From here, I would have the square root of 6 over 30, or the square root of 1 over 5. And whenever I take the square root, I have a positive and a negative. So I actually have 4 potential points of inflection there. So drawing my second derivative number line with those points there, my potential points of inflection, I had so -1 and then negative square root of 1 over 5, and then I would have positive square root of 1 over 5, and then I would have, extending my number line a little bit there, 1, okay, and I'm going to plug that back into my second derivative, and I am going to end up getting, which, and again, my second derivative was this, x squared minus 1, and then I had 30x squared minus 6. Okay, so I'm going to plug back in here. If I plug in a -2, I would get a positive times a positive, which would give me a positive there. Then if I plug in something in between there, like -0.5, that would be a negative here times a positive there, which would give me a negative. Okay. Then plug in 0, I would have a negative times negative is positive. That's an easy one. Plug in positive 0.5, I would have a negative times a positive, which would be a negative. And then if I plug in a larger number, both of those would be positive. There you go. So what that means then is I've got concave up, concave down, concave up, concave down, concave up. Okay? And so part C asked me for what values of x is the graph of f concave up. It is concave up from negative infinity, because I don't have any like interval endpoints, to -1, and from negative square root of 1/5 to positive square root of 1/5, and from 1 to infinity. And my justification is I just say because The second derivative is greater than 0. It's positive, so we're concave up. And here we get into the curve sketching part. Sketch the graph of f. So here we go. I am going to sketch this graph here. I'm going to think back to my original where it said plot any given points. I didn't have given points, but I did find the x and y intercepts. So the x and y intercepts, oh, I missed an x-intercept too. Sorry, if you were wondering earlier. -1, 0 would also be an x-intercept, right? Sorry about that, because that would also make this 0, okay? So I'm going to plot those. For the sake of this, I'm going to make my scale a little bit bigger. I'm going to make this a 1. So I'm going to make 4 boxes equal to 1, okay? And there we go. Okay, so I'm going to plot my x-intercepts. And then my y-intercept was at 0, -1. Okay, so I've got those places there. Then find the critical points and intervals where we're increasing and decreasing, and our relative max and min. So our relative min was here. And then if I look back at this number line here from my first, I know that we had negative, negative. So something was happening at -1. I had a horizontal tangent there, okay? So we were decreasing and then decreasing. So what that must mean is that I was coming down here, and then it must have flattened out and then gone back down. Okay, so you want to make it so that it's clearly like it's flattening out there. Then here I had a minimum, and then it was going back up to increasing, but I did have a horizontal tangent there, so it was increasing and then increasing. So what I like to do is I sketch this, and then I confirm my concavity. Okay, I just think it's easier to draw it with the increasing and decreasing, but then double check, make sure that your concavity matches as well. And our concavity, remember, we were supposed to be positive minus plus. Okay, so concave up. So yes, this is definitely concave up here. I'm gonna adjust this a little bit to make it a little curvier, right? So I've got that upward facing bowl. Then it does turn to be downward here, right? I've got like the top of a hill here. We don't have to complete that whole thing for it to be concave down, right? Just this piece here, that's half of a hill, so it is considered concave down. Then here I've got concave up again, happening with my minimum. Then I've got, so I might want to fix this a little bit just to make it really clear that it's concave down here. So concave up, concave down, and then concave up again. So this is probably like this split here where this is happening. That's at about that square root of 1/5 place. Right, so I maybe should have made it a little bit closer to the y-axis, but you get the idea. And same here. So your sketch does not have to be perfect. What it does have to do is include our important points. Our x-intercepts, our y-intercepts, and our minimums and maximums must be labeled clearly. And then our increasing and decreasing must be going the right ways. And then your concavity should be clear enough. It doesn't have to be perfect, but it does have to be clearly changing, making sure that we're paying attention to those horizontal tangents there, right? Those critical points that didn't switch here. So the critical point that didn't switch, but it still is a critical point. It still flattens out. Your slope is still 0 there. So making sure that those horizontal tangents are clear in those spots. And there you go. You just sketched a curve using all of that beautiful calculus knowledge, okay? So go ahead, go practice that. Make sure that, again, you're going through all of those steps. Don't forget about your asymptotes. Go back to note cards 4 and 5 if you've forgotten about asymptotes. Anytime you have a fraction, if you've got a denominator happening, check for those asymptotes. All right, have a lovely rest of your day, and I will see you all soon.